Have you ever stopped to think about the incredible, almost unimaginable power that's locked away deep inside the tiniest bits of matter? Well, today we're diving headfirst into that invisible, energetic, and kind of chaotic world of radioactivity. And we're gonna start with the biggest question of all. Right? It's a word we hear all the time. But what does it really mean for something like uranium to be radioactive? It's not some weird chemical thing. Nope. It's something way, way more fundamental than that. You know, when you really get down to it, radioactivity is basically just the story of an atom trying to chill out. Imagine you've built a tower of blocks that's just a little too wobbly, a little too unstable. What's it going to do? It's going to shed a few blocks to keep from falling over. And that process, that act of falling apart to find some stability, that's radioactivity. To really get what's happening, we've got to zoom in and peek inside that unstable core, the nucleus. It's a pretty crowded place in there, but there are a couple of key players you need to know. Okay, first up, you've got the atomic number. We call it Z. This is super simple. It's just the number of protons. Think of it like an atom's social security number. It's what defines it. If you have 92 protons, you're uranium, period. If you have 6, you're carbon. That number is the element's identity. Then you've got the mass number, which we call A. This is just the total count of the heavy stuff in the nucleus. That's all the protons plus all the neutrons. These guys together are called nucleons, and the mass number just tells us how much that nucleus weighs. And here's what's so wild about this whole thing. It is completely, totally spontaneous. You can't speed it up, you can't slow it down. You can't start it or stop it by heating it, freezing it, crushing it, or mixing it in a chemical reaction. It's a purely nuclear event, happening deep inside that core, totally sealed off from the outside world. So when that unstable nucleus finally decides it's had enough, it kicks off this process we call radioactive decay. This is the main event, the actual moment of transformation. So what is it? Well, it's that unstable nucleus literally spitting out some kind of particle or a burst of energy, which is what we call radiation, so it can turn into a different, more stable nucleus. It's an atom changing its own identity to find some peace. So what exactly is the nucleus throwing overboard to lighten the load? Well, it turns out it has 3 main options, 3 main types of radiation it can emit. All right, let's meet the team. We call them alpha, beta, and gamma. You can think of them as the ABGs of decay. Each one is a totally different strategy for an unstable atom to get itself sorted out. First, you've got alpha decay. This is the heavyweight option. The nucleus just ejects a chunky particle made of 2 protons and 2 neutrons. Now, if you know your elements, you'll recognize that that's basically a helium nucleus. And because it lost 2 protons, its atomic number drops by 2, and poof, it's a completely different element now. Next up is beta decay, and this one's a bit of a magic trick. Inside the nucleus, a neutron suddenly decides to become a proton. In that process, it shoots out a tiny, high-speed electron, and that's our beta particle. So think about it. The nucleus now has 1 more proton than it started with, so its atomic number goes up by 1. But since it also lost a neutron, the total mass number doesn't change at all. And finally, there's gamma emission. Now this usually happens right after an alpha or beta decay. The new nucleus is stable, but it's still a little overexcited. So to calm down, it releases a burst of pure high-frequency energy, a gamma ray. No particles are lost, so the atom's identity doesn't change. It's just letting off some steam. This chart really lays it all out. Look at the alpha particle. It's big, it's heavy, it's got a positive charge. That makes it a real bully. It's fantastic at knocking electrons off of other atoms, which is what we call ionizing power. But because it's so big, it can't get very far. A single sheet of paper will stop it cold. Beta particles? They're tiny, negatively charged, and can zip right through that paper. And gamma rays? Whoa. They have no mass, no charge, just pure energy. They're not great at ionizing, but they're incredibly hard to stop. You need thick slabs of lead or concrete to block them. And you can actually see these differences in action. If you fire a beam of all 3 through a magnetic field, their true colors show. The big, positive alpha particles get nudged one way. The super light, negative beta particles get yanked hard in the opposite direction. And the gamma rays, since they have no charge, they just sail straight through, completely unfazed. Okay, so we've got the basics of how one atom decays. Now let's scale things up, way up. Let's talk about the 2 most famous nuclear reactions of all, fission and fusion.
This is where we go from a tiny atomic event to unleashing unbelievable amounts of energy.
At first glance, they look like total opposites. Fission is all about splitting a big, heavy nucleus into smaller pieces. Fusion is about slamming small, light nuclei together to make a bigger one. But here's the secret. In both cases, the final products are more stable than what you started with. And that tiny difference in stability, it gets released as a massive, massive burst of energy.
Fission, this is the reaction that runs our nuclear power plants. You take a big, wobbly nucleus like uranium-235, and you hit it with a neutron. That's enough to make it split apart, releasing energy and, this is the crucial part, a few more neutrons. Those new neutrons then fly out and hit other uranium atoms, which split, releasing more neutrons, and you get a self-sustaining chain reaction.
And fusion? Well, this is just the power source of the entire universe. Deep inside the sun, the crushing gravity and insane heat are forcing hydrogen atoms to fuse together into helium. That process releases the phenomenal energy that warms our planet. It's the very same reaction that forges all the heavier elements in the cosmos. So it's pretty clear we've managed to unlock this incredible power from the heart of the atom. But, like any truly great power, it's a double-edged sword. It comes with incredible promise and very real peril. On the one hand, the promise is just immense. We use radioactivity in medicine every single day for diagnosing diseases and treating cancer. It's a vital tool for scientific research. It's used in all sorts of industrial jobs. And we even use it to look back in time, figuring out the age of ancient artifacts with carbon dating. But the other side of that sword is just as sharp. High doses of radiation can cause devastating biological damage. We have to deal with the risk of radioactive fallout from accidents, and we face the enormous challenge of figuring out how to safely store nuclear waste for thousands of years. Heck, we're all exposed to a tiny bit of background radiation every single day. So, from the quiet random decay of a single, unstable atom to the raging furnace that powers the stars, the atomic nucleus holds a universe of power. We figured out how to unleash it, for good and for ill. That power is in our hands now, and it leaves us with one of the most profound questions we have to answer. What are we going to build with it?